Hello everyone. Welcome to another video. Last lesson we discussed what momentum and impulse were and described what they were mathematically, where momentum is just equal to mass times velocity of an object, and the impulse was defined as the change in the momentum experienced by an object. And we also wrote an equation down for that, which was mass times the change in velocity. And we also discussed the relationship between force and impulse. So today we're going to be building on that, and we're going to continue discussing momentum. Let's start today's class by considering a scenario. Let's say we have two objects. I'll call this object A, and I'll call this object B, and let's say they're on this course to colliding with each other. We want to know what would happen to these objects after their collision. What motion would they experience? And this is actually where the conservation of momentum comes into good use, because it gives us an insight into how the object will behave after a collision. So let's look at the definition for the law of the conservation of momentum, and I'll bring that up on my screen now. The law of the conservation of momentum states that in an isolated system, the total momentum of that system is conserved if there's no external forces acting on it. So what does this mean in everyday language? Well, essentially, in a closed system, the sum of all the momentum before a collision is equal to the sum of all the momentum after a collision. And I can write that down mathematically as the sum of all the momentum before, and I'll write B for before, is equal to the sum of all the momentum after. In fact, B and A might become confusing later on, so let me call this initial, so I for initial, and I'll call this subscript F for final. So let's go ahead and put an F there. And by the system, I simply mean the bit of space that we're looking at. So we wouldn't be concerned with what's happening outside of our space. So if I'm looking at this section of space here, I'd only be concerned with what's happening with A and B in that system. I wouldn't be concerned of anything that's going on in this space or going on in that space. And that's because this is outside of our system. So let's go ahead and apply this to a question. Let's say we have two toy cars, and I'll just draw them as blocks. So let's say we have one toy car over here, and we have another toy car over here. And we'll label them as A and B. Let's say the mass of A is 3 kilograms, and let's say the mass of B is 4 kilograms. The velocity of A is equal to 3 meters per second, and let's say the velocity of B is equal to 2 meters per second. And let's say they're on a collision course toward each other, so A is traveling toward the right and B will be traveling towards the left. And let's say after the collision they remain locked together so that they travel with each other. So if I sketch that out, it would look something like A combined with B, and let's say B is a little bit bigger because it's 4 kilograms. But how do we know which direction this is going to travel in? Well, I like to think about these problems as me imagining that I'm taking a beforehand picture and an after picture, and I'm calculating the momentum in both of these pictures. So let's begin by assigning a direction, and we'll take the right as positive, and it doesn't matter which direction you take as positive as long as you're consistent throughout. And let's calculate the momentum in my before picture and my after picture. Now we've just learned that the momentum before is meant to equal the momentum after. So let's write that down. So let's say the momentum before, so initial, is equal to the momentum after, which is our final. So we have a momentum associated with A, and we have a momentum associated with B. So to calculate the momentum associated with A, we just go MA times VA, and we add that onto the momentum associated with B. So we'll go MB times VB. And because we know these masses are going to be locked together and move together after the collision, we can say the masses of AB times the velocity of AB, so the combined velocity, is going to be the momentum of the system after the collision. So let's continue by substituting our values. So MA is 3 kilograms, VA is going to be 3 as well because we've said the right is positive. So we add that onto MB, which is 4, and we times it with VB, which is going to be negative because it's moving towards the left, so that'll be negative 2. And that will equal our combined mass, which is going to be 3 plus 4 times the velocity, the combined velocity of this system, which is AB, of these two masses. So let's multiply these out. So we've got 9 minus 8 is equal to 7 VAB. And if we solve that, we get VAB is equal to 1 on 7 meters per second, which is 0.143 meters per second. And because we have a positive answer here, that means the system must be moving towards the right. So I'll put down that direction, right. So VAB is equal to 0.143 to the right meters per second. So we figured out how to apply the law of conservation of momentum. Let's take a closer look at how momentum transfer actually occurs. So say we had two cars, which I will draw on a new section of this whiteboard. So let's call this one car 1. So car 1. And let's say we have another car as well, car 2. And let's say car 2 is at rest, so I can say V2 is equal to 0, and I'll put I there just to signify the initial condition. So V2I will equal 0, and car 1 will be about to collide with car 2. We know that once they collide, car 1 will exert a force onto car 2 and cause car 2 to accelerate. So let's bring them in contact and show that. So car 1 imparts a force onto car 2, where this is car 1 and that's car 2. Similarly, car 2 will exert an equal and opposite force onto car 1, and that's in accordance with Newton's third law. And since the time the cars will be in contact is the same for both of them, if we go back to our impulse equation, which is del P is equal to force divided by del T, the magnitude of impulse here and here for both the cars will be exactly the same. So let's say car 1 has a momentum of 1,000 kilograms meters per second, and it's bumped into a stationary car, which is car 2, which would have a momentum of, and let me label this as P1I and this one as P2I, of 0 kilograms per meters second. And that's because this car 2, will be stationary at the initial condition. And let's say that after the collision, car 1 loses 300 kilograms meters per second of momentum. So let's say our final condition, P1F, is equal to 700 kilograms meters per second. Well, then that 300 kilograms meters per second of momentum would actually be imparted into car 2. And that's in accordance with the law of conservation of momentum. So we can see that the momentum before the collision would be the exact same as the momentum after the collision, such that the momentum gained by car 2 would be equal to P2F of 300 kilograms meters per second. And this would remain the case unless there was an external force that acted upon this system at any time. Now that we've seen how momentum transfer works and how the law of the conservation of momentum manifests itself, let's go ahead and discuss elastic versus inelastic collisions, which I'll bring up on my board. An elastic collision is one where there's no loss of kinetic energy, meaning that the kinetic energy before the collision will be equal to the kinetic energy after the collision. So not only would we have to consider the law of conservation of momentum, but we'd also have to check the kinetic energy of the system before and after the collision to ensure zero kinetic energy was lost. So if kinetic energy in an elastic collision is conserved, it would follow that inelastic collisions are those in which kinetic energy is not conserved. So the kinetic energy prior to the collision is not the same as the kinetic energy after the collision. And this loss in kinetic energy can usually be due to the production of heat due to the collision, or sound, or light. But the momentum in the entire system across both cases has to be conserved for elastic and inelastic collisions. So I hope that gives you an insight into what momentum is. We'll go into further detail and we'll do some practice questions next lesson. So thank you for joining me, and as always, catch you at the next one.